It's a great pleasure to have Professor Adolfo Grushin to come and talk about his recent work in topological insulators. So Adolfo is a senior researcher, a group leader at Institut Néel in France. He received his PhD in Madrid. Is that correct?
That's correct.
With the very famous Spanish theorist, I think it was Maria Vosmendiano.
Right.
And then he's basically working on all sorts of things. Sometimes, very kind of field theory, very heavy, but actually he's very well known for his work in nonlinear response theory, in particular work on these photocurrents in wild sim metals. But he's going to maybe tell us a little bit about a new direction that he's been taking in the last year plus. I guess in the last 2 years. I guess.
Yeah, more or less. Yeah.
2019 about amorphous topological insulators. Is kind of a very broad new field, and so without any further ado, let's welcome Adolfo to this condensed matter seminar.
Yeah, thank you, Justin, for the invitation. Too bad I'm not in Singapore because I've never been, and it would be amazing to be there. Next time, I'm sure you'll come at some point. Yeah, this pandemic will last some time, but you'll come eventually. Yeah. No, it would be great. I mean, definitely feel free to invite me in person. I would be very happy.
Point taken. Yes, noted.
But nonetheless, I'm very happy nonetheless to see some familiar faces and tell about this. Indeed, a bit of a new direction I'm taking, a bit out there, but still I hope to convince you why this is interesting and not kind of like a repetition of what we already know. Okay, so I'm gonna indeed talk about amorphous topological insulators. And if you kind of want to just read about it and maybe like not digging too much into the equations, there's a book chapter I wrote recently. The book is actually about just normal amorphous systems, but they were curious about this. So there's a kind of out there last chapter about topological insulators in amorphous systems. That's why what I'm gonna tell you about today. And then most of the things I'm going to talk about are basically in these two papers. One of them that is particularly tricky to convince the referees, but I guess that's nice because there's some discussion, and this means that at least that it's not boring, which is I think I'll try to give you a reason why it's taking so long. But anyway, so you'll see for yourselves. And okay, so basically amorphous topological insulators. So why on earth we want to study amorphous things? We're solid state physicists. We like order, symmetry, and this sounds like complicated, dirty, and weird. So why would you want to study this? And in fact, it's even more complicated than this, because if you look at typical solid state textbooks, I studied Ashcroft and Mermin, and amorphous solids are, I think, not mentioned at all, even though they're solids. And in fact, this is shared also, funnily enough, with topological phases. Topological phases were not known back then, and so there's not, or at least not widely known. Possibly the work by Larringer and Karplus was there out there already, but definitely not mainstream. So those two are kind of the main absence of in solid state physics books. So then you're then okay. Not only you have to study this dirty, strange thing, but also you cannot look into your favorite books that you studied in undergrad. So again, why would you complicate your life and also go beyond what we already know in crystals? So to start, I'm gonna just briefly mention why we're interested in topology at all in solids. And you might see different motivations depending on the type of talk you go to or the type of background you have. And so here I'm gonna explain why would you be interested in topological phases, whether you're a condensed matter physicist or a high energy physicist or more leaning into applied science. So the bottom line of topological phases is that we cannot understand what happens in solids with only symmetry breaking and band theory. So you have probably studied that if you create a solid, maybe out of a gas or a liquid, you either well, you crystallize in a lattice, typically that's what you've been taught, and you either get localized orbitals or delocalized electrons. And so these we call insulators and metals, and basically their band structure, the energy versus momentum of the electrons. In an insulator, you would require some certain energy to imprint to the electrons that we call the gap to actually make them conduct, and that's why insulators, if you just try to conduct to pass a current, they would not respond because the band is completely filled. So there's an energy price you have to pay to actually pass a current through an insulator. But in a metal, the bands are partially filled, and you can pass a current no problem. It turns out that you can find insulators and even metals with very similar band structures, but very different properties. And this is kind of why topology started. Yeah, perfect, thanks. And so, and the what is different in topological phases is that
yeah, you just muted yourself, Adolfo.
I know, I don't know, somebody muted me, I think.
Oh, sorry, wow.
Yeah, no, it's okay. Okay, so yeah, so what I was saying is that if you can find two insulators with essentially the same band structure and a different response. What I mean by different response is you pass some electromagnetic field, you apply an electromagnetic field, and you see responses that are universally quantized. What it means is that these responses, like let's say these currents, would depend only on fundamental constants of nature, let's say E squared or the Planck's constant, and they would be independent of material parameters like density of impurities or something. Even if they're dirty, they would respond the same way. And this kind of puzzled a lot of people, or let's say draw a lot of people into the field, because it was a very, very universal type of behavior. And as physicists, we like universality, we like very generic principles, and this is what's behind topological phases. Now, if you're a high energy physicist, you very quickly realize that the underlying, let's say, quasi-particles that are the descriptions of these topological phases are very similar to relativistic quasi-particles that we know from particle physics. But here the story is a bit different, even though the dispersion here, it could look, for example, like the dispersion of light, linear in momentum, but for charged particles, electrons, you can play with their environment essentially. And for example, you can create this description or describe these phases in different dimensions, like 1D, 2D, 3D, or even more. With artificial systems, you can go even to higher dimensions. You can add terms that you wouldn't have in typical particle physics theories, like topological terms, or you can break symmetries that they're there in the real world, but not necessarily inside a material, which is like, for example, Lorentz symmetry. So this brings a lot of rich behavior that you can study in these materials. That's part of my research as well, but I'm not going to talk about it, but just like as a motivation. And then topological phases are among the most robust phases in nature, and the reason is the following, and here's my working definition of a topological phase, is something that has an insulating bulk. So electrons do not conduct let's say in the inside of the material, but they conduct at the edges or the boundaries of the material. The surfaces or the edge states are conducting. And so by kind of separating degrees of freedom, you can make use of these states for whatever you want to do with them. In particular, for example, you can imagine, let's say, spin up particles going one way, spin down particles going the other way, and not interfering with each other, kind of like in two separate highways. And this, by separating degrees of freedom, we can in principle use them for computation. And since they don't talk to each other, they remain robust. And so that's kind of the excitement in terms of applied physics. So just keep in mind this working definition of topological phases. Now, why? Maybe you have heard about topological phases, but maybe why we're interested in amorphous physics beyond the fact that we all have windows and glass is amorphous. So so why would you care about this? Now, it turns out that amorphous solids have really interesting properties compared to crystals. One of them, which I find pretty exciting, is that they can have higher superconducting critical temperatures. For example, bismuth is barely superconducting. Actually, it was really recently discovered that it was superconducting with 10 to the minus 4 Kelvin critical temperature. But then you have a 10 to the 4 increase in the amorphous case, and this is not an isolated, maybe not common, but it's not rare. It's not also rare that there are elements and even compounds that have very low crystalline critical temperature, but very high in the amorphous, or relatively high compared to the amorphous. And the field of disordered superconductors has been like very much explored by many people because of this reason. Try to understand the mechanisms behind it. Now, if you like either amorphous or topological insulators, you might want to include amorphous materials simply because most materials can be made amorphous, and usually this is actually cheaper to grow something that is amorphous than crystals, than very clean, very nice crystals. And so so basically, if you cool any material fast or to low enough temperatures, you can get an amorphous state. And that's already interesting if you want to find all the possible phases or materials that display a certain property. Now, oops. Now, if you're going to more kind of out there type of motivation, in fact, amorphousness can also be thought about gravity in a way. And the reason is that, as I was saying, this relativistic descriptions of topological phases, you could change kind of the background of where they move. In particular, if you strain them, if you strain materials, you can kind of map, for example, in graphene, if you strain graphene, you can kind of map the theories that describe them into theories that look like Dirac fermions in curved space-time. And if you have an amorphous material, it very much, you can very much describe at least the long wavelength modes as something that is coupled to some metric, so underlying gravity that kind of changes in space, but it's frozen. And so this, some people call it quench quantum gravity, and is also a topic of exploration. So this is quite exciting as well. And now, if you're more into applied stuff, as I was saying, amorphous solids made their way into technology quite quickly because they were cheap and scalable. And in particular, if you have used ever one of these calculators, maybe the younger people in the audience have not, but at least I have. This tiny solar cell here is made of amorphous silicon, which it might be not the most efficient solar cell in the world, but it's definitely cheaper, and you can integrate it in a calculator that you can sell for not a lot of money. And so, and in fact, also in semiconductor technology, they've been using amorphous systems, and in particular semiconductors for a long time. Right. So then, okay, I hope this kind of gives you a motivation of why we should look for amorphous solids, why we care about topological phases. And so now we have to find them. And so to find them, we need to know already first how to find the crystalline ones, which I'm going to tell you right now. So I'm going to give you a few examples and just visually show you, which I think is all, I think it's kind of goes a bit understated how beautiful these things are. So examples of topological crystals. One of the most modern ones is tungsten ditelluride, and this is the example that I was alluding to before. You have an insulating bulk and some conducting edges, and the way we know it, or one of the ways we can know it, is by shining light and see where it reflects. And so here you see, so there's a substrate, there's tungsten telluride, and they shine, I think, microwave light, and they look where it reflects, and it reflects mostly at the edge, indicating edge conductance, or at least edge metallicity. And to show that these are indeed topological states requires a bit more effort, but nonetheless, and there are transport experiments that you can do. But here's at least a visual image of the edge state. Now in 3D, so this is 2D bulk and 1D edge conduction. And in 3D, you have bismuth selenide is kind of the textbook example of a topological insulator, and it's if a chunk of material that is ideally insulating in the bulk. And at the surface, it has this really nice Dirac cone, we call it, of conduction electrons, conduction because it has no gap. And so you can nicely visualize it in experiment. This is an experiment where you shine light and collect electrons and measure their energy and their momentum. And you see very nicely this Dirac cone. And so we have a bunch of examples like this that are pretty nice. This we call strong topological insulators. Strong as in they don't require any spatial symmetry. They are protected by time reversal symmetry, or by basically discrete symmetries. They're called discrete symmetries, symmetries that are either well, either time reversal particle hole or the combination of both. And in 3D, you know, the example is bismuth selenide has this Dirac cone. I already told you about tungsten telluride. Actually, the first to be discovered was the quantum Hall effect, which has just, you know, single conducting edge states, and it breaks time reversal symmetry. So you need a magnetic field or something magnetic to realize it. It was discovered in the 80s. And in 1D, you have another type of phase where you have it involves superconductivity, and you have what we call Majorana fermions at the end. And this has been also actually one of the hardest. it's still being kind of debated. One of the hardest ones to actually figure out if we really have that topological phase. But nonetheless, you know, people we've started studying these strong topological insulators, and then thought that perhaps by adding extra symmetries, you can get different states. And so this turned out to be a huge field by itself. So if you add lattice symmetry, so you start considering the symmetries of the lattice you have, you can actually protect new topological phases. For example, instead of having one Dirac cone, you can have two. If you wouldn't have these other symmetries, these two would, let's say, couple to each other and gap out and create an insulator, thus by not being a topological insulator. Because it would have insulating surface, not conducting surface. But with this extra mirror symmetry in the case of tin telluride, you can have two Dirac cones instead of one, so double the conduction. You can have even more weird things in bismuth. For example, you can have this helical or this spin up, spin down going in opposite directions along the hinges. So there's some evidence, experimental evidence for this. And in 2D, you can have corner states that kind of stay there pinned at the corners. And so these are all require lattice symmetries, and this have been labeled as topological crystalline insulators, and they have been observed in real materials. And just for the sake of completeness, I'll say that there is also topological metals. I won't really describe them in this talk, but just for completeness, they have this relativistic type of dispersion, but now in the bulk. And they also have edge states, so they kind of fall a bit outside of the definition that I was telling you about topological insulators. These are topological metals, so they conduct in the bulk, but nonetheless you can associate some topological properties to them. And these all these systems have been found in anything, essentially anything that can have a dispersion relation. So anything that you can say, okay, we have some bands, and then we can see a gap within this band. This we would associate to an insulator. And if you see that the bands kind of close or they're gapless at the surface, then that would mean that it's a topological insulator, or like a topological band structure, if you want. And so of course in the quantum in solid state, we can find them. We can find these materials which I've been talking about. You can also create them with using arrays of cold atoms and kind of simulating material. Or in anything that has waves, really. Now, the important thing to realize is that, okay, we have, first in the field, we had a bunch of examples, people started finding them, but at some point it became clear that we needed some systematic way of finding topological insulators. And the way to systematically find them is the following. Let's say you give me a space group, which just means a lattice, which is certain symmetries, translations. So here I show the honeycomb that has some translation, somehow has some rotational symmetry, etc. And now you tell me which orbitals I have to put in this lattice. So S or P or D or whatever. And then with these, you have to tell me also where I put the orbitals. So you can have, I could put them all at the center, for example, or I could put them at the sides, at the edges. And so this would give me, with this information, I can construct a band structure. So E versus K for these electrons in these orbitals. And in fact, since I have symmetries, then symmetries, what they do for you is that the Hamiltonian kind of block diagonalizes. So you can label the bands with symmetry eigenvalues, because you can diagonalize both the operator that gives you the symmetry and the Hamiltonian. And so specifically at certain momentum points. And so you can label, let's say with inversion symmetry, like x to minus x, the bands. And in fact, it turns out that when you have these type of symmetries, you can know which topological phase you have in the following way. So it's essentially multiplying these pluses and minuses of field states. So the way it goes is that you give me a lattice, give me the orbitals, give me the place where they go. I plot the band structure, label the band structure with the symmetry eigenvalues, and then calculate what we call topological invariants, which are just numbers that if, let's say, if 0, it's not a topological insulator or a trivial state. If it's 1, it's a topological state. And then from that, you get these universal responses that I introduced at the beginning. And so, for example, when you have time reversal symmetry and inversion, so inversion just x to minus x, time reversal t to minus t, so nothing magnetic, and some inversion symmetric crystal, you can label your eigenstates with inversion eigenvalues, multiply them all, and you get either -1 or +1. If you get -1, it's a topological insulator. If you get +1, it's not. And that's a topological invariant. And so you can do this for essentially any topological phase, and that's how people find them right now. And it's so automatized that you can actually go online into certain websites. So this was developed around 2019. There are a few websites here. I'm just showing one where you can, choose. Let's say I'm interested in bismuth selenide, so I pick bismuth, I pick selenide, I pick selenium, and then this website immediately tells me all the compounds that I could form or that I at least tabulated in material databases and calculates the invariants for me. And the one that I was showing before is it's right here. It's a bit more complicated which numbers belong to what invariant, but this is basically this 3 means this -1 in my previous slide. Anyway, so this is I mean, if you with a bit of effort of understanding the notations, you can in principle go to these websites and find topological states. So topological crystals. So and then at the beginning. And since the very beginning, people started wondering how robust they are to disorder, to imperfections, because I told you that they were robust, that they were universal, but how robust and how universal. And so here I just plot or schematically draw some types of disorder you can find in materials. For example, electrons hop in this lattice, and they might find that the hopping is not exactly the same wherever they go, and they can find some bond disorder, we call it, or on-site disorder, some on-site potential that kind of changes with space. Or the one that will interest me later, some geometric, or previously called topological, but maybe forget about the topological, just call it geometric disorder, which means that the connectivity of the lattice is different to the crystal. So all these things can appear together, and we should understand how they affect topology. So on-site disorder is one of the most studied ones, and we actually know pretty much what it does. It can destroy topological phases if it's too strong, but in fact, before destroying topological phases, it can actually enhance them. So if you plot, let's say, the energy of the electrons as a function of the strength of this disorder, how much disorder I put at each site on average, you'll see that at 0, well, here where I start, it's an insulator, but then as I move, it's insulator, but suddenly something changes in the system, and basically the gap is closed and reopened in a certain way, and you have a topological Anderson insulator. So which just means that disorder has driven a trivial insulator into a topological insulator. And this was shown in 2009. You can imagine that there's maybe a trivial insulator very close to the transition, and kind of disorder plays with the parameters in such a way that it drives the transition to a topological state. But of course, if you increase disorder too much, then it will become trivial again. And so disorder in some intermediate regime can enhance topology if you want. And people then, or now, are getting quite creative.
Hey, Adolfo, I had a quick question about the topological Anderson insulator. I think I heard about it some time ago, but I never really understood it. So there's no real spectral gap that opens, right? Is it just a mobility gap that opens?
It's a mobility gap, yeah. It's a mobility gap. Yeah.
I see. And so somehow, because of topology of the band structure, the edge states just don't want to have a mobility gap. It's just the bulk that wants to have a mobility gap.
I think you can understand it as like or the way I understand it is like if you take the model without disorder and then add disorder perturbatively, the model has some parameter that drives the transition. And as you add disorder, let's say perturbatively in some expansion in Feynman diagrams, then the first correction, if you want, or the biggest correction is to actually comes with an opposite sign. And so it inverts the gap. I mean, that you're not guaranteed really to have this all the time. But if you're close to the transition, certain types of disorder, I guess, depending on the symmetry class and so on, can actually help you. But then as you increase disorder, this might go away.
Okay, thanks.
Yeah, thanks for the question. Yeah, again, interrupt me anytime, please. Okay, so right, so then people started getting quite creative and for example asked, okay, can I have a quasi-crystal with topological phases? And indeed you can have. There's an example here with C8 symmetry, so 8-fold rotational symmetry. That is impossible in a crystal. There are no 8-fold rotational invariant crystals, but there are quasi-crystals. So here's one. So nonetheless, maybe not the most realistic quasi-crystal, but nonetheless very very striking to see something that cannot be done in crystals. Now, people also went to fractals. Again, this is not something periodic, but and showing that you actually have edge states in fractals, it can become a really subtle issue. And there's a bunch of discussion where this is actually topological and which dimension. The idea is that I told you 3D, 2D, 1D, but fractals are kind of in the middle. So that's kind of their interest. And lastly, I cannot help mentioning that Maya superlattices, which are also quite now in fashion, they are not strictly periodic. And so these are also states where you find topological phases, but translational symmetry is not precisely there, although you can at low energies, you can kind of recover it and it works fine. But nonetheless, like just to signal that topology itself is not restricted to translational invariants. We can find it it does not require really, maybe you lose all the symmetries of your lattice, but translational symmetry is not strictly required for topological phases to exist. Okay, so now we have this. Now we can ask, where can we find the topological amorphous solids and what type of properties beyond crystals can they have? And the first example was around, beginning of 2018, end of 2017. In this I really recommend this paper, really well written and has a lot of interesting videos that I'll show in a second. They basically started with, so it's a theory experimental paper. They started with some random points. And now you construct what it's called the Voronoi diagram, which just means you find the line that's equidistant to given 2 points, and this creates some triangles that if you connect the dots, then you immediately get a 3-fold coordinated lattice, and this lattice is random, so it's kind of like the random version of the honeycomb lattice, if you want. It has hexagons, pentagons, and whatnot. And in this lattice, they thought of every point, and they actually built this as a gyroscope. So basically a magnet that turns, and these magnets kind of interact with each other just magnetically, but you can think of them as 2 lowers or as some sort of spring coupling these sites. And they knew already that when they created this thing out of just a honeycomb lattice, you would have edge states. And the reason is that you're kind of breaking dimersal symmetry, and this kind of imitates some model that we know that has edge states. And in fact, it works also in the amorphous lattice. You excite these gyroscopes at the edge, and you get an edge mode. And here's the video to show it. So here's the gyroscope is excited here, and then hopefully you can see that it mostly goes in one direction. Of course, there's some excitations going on. The system is finite, but nonetheless, most of the propagation happens at the edge. And more or less at the same time, although this is kind of not very fair because one was published at the beginning of 2018, the other one at the end of 2017. But more or less at the same time, only theory paper showed as a proof of principle that if you take a random set of points and you couple points up to a radius r with some decaying function, they would show also edge states here. And so both of these papers basically show that you can have topological phases in amorphous systems. Those, as far as I know, the first papers. Okay, so now the problem, I mean, this is great, but the problem is, how do we find actual materials? Because now the space group is gone. No space group. There's no long range order. That's the definition of an amorphous lattice, is just no long range order. Orbitals are still there, but you don't have symmetries, or you don't have like some translational symmetry to actually plot the band structure. You cannot plot E versus K because K is given by translational symmetry. So what are the symmetries of amorphous matter? And in fact, you can kind of separate two types of symmetries. I'm mostly going to talk about local symmetries, but average symmetries are also interesting. And to visualize local symmetries, I think it's best to actually see with your own eyes an example. And here is amorphous graphene. So this is taken from an actual experiment, also a very nice paper. And you can see, so this is a transmission electron microscope image that that they colored on so that you could actually see which atoms are where, but it's a real experimental image just colored over. And you can see basically a few properties. So one is fixed coordination. So each atom mostly has the same coordination as in graphene. Each atom has 3 neighbors. There's some points where this does not happen, like here, but if you look at, I think this is the only example in this image. If you look at the rest of the lattice, most of the sites are connected by 3 neighbors. So there's nearly ideal connectivity. There's always some defects, but mostly it's every atom is connected to another atom. The bond lengths are pretty much peaked at, so blue is normal hexagonal graphene, while red is here amorphous graphene. So the bond lengths are wider in distribution, but they're peaked at the carbon-carbon length. So basically the short wavelength, sorry, the short distance physics is given by chemistry, right? So the carbon-carbon length is still the same. And so that means that, okay, there will be some fluctuations, but the average would be still the same. And this kind of upturn is just the second neighbor peak that you're seeing. Bond angles kind of the same, peaked in graphene, normal graphene at 120 from the hexagon, and now we have a bit of a wider distribution, but nonetheless peaked at the. So the local order is very much the same as in the crystal. That's my point. It's just a bit the distribution is wider, but the local order still exists. So my point with the slide is that amorphous solids are not a random collection of points. They have some local order. And you can see also that there are crystalline regions coexisting with amorphous states, with amorphous regions, and this is also seen in experiment. So the first generation of models, let's say, was to show that amorphous topologies can actually exist, but now we have to do a bit better to go to real materials, and here's the generation 2 of models would have to take into account that in amorphous solids, you have actually a similar environment to the crystal, meaning that you have still 3-fold coordination number. It's just that now you can have hexagons or pentagons or whatever. So the connectivity is different, but the environment is similar. And this local environment actually allows you, as I will show in a second, to define some sort of symmetry indicators, just as I was telling you before for crystals, that can help us identify topological phases in an easy way, and also in any dimension, really. So let's see how that works. The bottom idea is old. It's from Byron Thorpe, who studied a lot of amorphous silicon and silicon oxide. And in amorphous silicon, what you have is tetrahedral structures where again the chemistry dictates that every silicon has 4 neighbors, but they're kind of randomly distributed. And so they thought about this very simple model where in a tetrahedron the hopping strength would be V, so that's the probability of electrons hopping within a tetrahedron, And between tetrahedra, you have a hopping W. So only 2-parameter model. And now you want to plot the spectrum as a function of, so the energy as a function of V over W. And okay, so if V is 0, so then this hopping here is 0. And so you only have dimers. By dimers, you know that those dimers have inversion symmetry. And so they would have bonding and anti-bonding states. So all the states would be collapsed at 2 different energies. And as you increase W, these states would hybridize and open up into bands, where actually Weierthorpe noticed that the band edges, so the contours of these bands, so here, these gray areas are full of states, but these contours of bands are still good symmetry eigenvalues of inversion, which is kind of the well-defined symmetry here. So if you pick a state at random, it would not be inversion symmetric, but if you pick one at the edge of the band, it will be exactly symmetric. And so what other people also showed is that you can follow these band edges analytically in this particularly simple model and see where the gaps are analytically. Okay, so then we took this idea and we tried to construct a topological model, or Quentin and then worked to do this. And we constructed several models, and here I'm going to show one. And this is the following. It's a model where you have, at each side, you have a triangle. So here's a zoom of the triangle. And these sides are connected, again, with hopping W. But within the triangle, the hopping, instead of being only V, is V with some phase. This means that there's some, you can think of it as some little magnetic moment at the side that creates a little moment and breaks the universal symmetry. So we're after a topological phase called quantum Hall, or Recherche insulator phase, with coordination 3. So again, what we're trying to preserve here is that every site has coordination 3. And the nice thing about this model is, again, you can use the power of its simplicity in a way to capture where the gaps are and label the bands by symmetry. And so this is what we do here. So here, this limit is, again, V equals 0. So you see bonding and anti-bonding, and then this states kind of as before in the Weierthorpe model, kind of like hybridized. But nonetheless, if you follow kind of the contours of these bands, they would still be good eigenvalues of inversion, basically plus and minus eigenvalues of inversion.
I had a small, quick question here. So you obtain these band structures that you're showing here with these density of state stuff. That was through a tight binding model. Yeah,
exactly. So you have to think that every site, basically so there's a tight binding model in this precise lattice that I'm showing, and in every site, even though the distribution, the lengths are different, the hoppings are actually the same. So every site has this blue hopping is W, and the green hoppings is V times e to the phi, where e to the phi is this phase that I'm showing here with an arrow.
And that phase factor is that disordered, or is that phase factor the same?
So it's not disordered right now. It's not disordered. No, it's so the idea is to isolate the effect of let's say geometric disorder. Like, because we know that when you disorder the phase, when you disorder the hopping, you basically repeat again the story of the topological Anderson insulator. So we're not interested in that. But here, this disorder, this geometric disorder, in a way, if you want, it's in the same symmetry class. So it doesn't, it doesn't add or break any other symmetries. Just it's also going to create, for example, a mobility gap. You're going to have states that are localized within the gap if you just disorder the lattice. So
So help me with this a little bit. So you have a tight binding model with a hopping parameter the same as a non-disordered system, and the phase is the same. Then what's different then?
The connectivity of the lattice. So if you think of this as the Kagome or decorated honeycomb, if you want, then a decorated honeycomb with triangles, then all of them would be, let's say, hexagons. you know, all of them, they will all look like this site.
I see.
However, here we have loops that are maybe even or odd depending on the loop.
Got it. I got it. Yeah.
That actually enters like a disorder.
Great. Excellent.
Okay, great. Thanks. Okay, so here we have this bond inversion type of symmetry for the band edges, but we also have this C3 rotation within a given site, because since all sites are equivalent, we can rotate them and assign a symmetry label also to this to the states based on this symmetry. And so this is what I color here: blue, red, and green. You can forget about the dashed lines for the moment, but basically you can see that the band edges always have some defined color, and this actually you can show analytically that for this symmetry as well, the band edges are still a good symmetry. It's still eigenvalues of C3 symmetry, which is the symmetry that turns each orbital into another. And not surprisingly, we can find, because we broke dimensional symmetry in a 2D model, we can find a part of the parameter space where you have an edge state in the lattice. And from previous works, we knew how to calculate the topological phase diagram depending on, let's say, phi and W. You can calculate what's called a local term marker. So something that it's a topological invariant for disordered systems in 2D without dimensional symmetry. So very specific to this model. You can calculate the phase diagram and see that you have a topological phase with an index 1, -1, or 0, depending on where you are in the phase diagram. Now, the problem with this is that, so it's a numerical method. You need to calculate the whole spectrum, or the whole field spectrum, sum over it, and generate this phase diagram. This was already known. The problem is that it's not really generalizable to other topological phases, and it's actually relatively slow. So this, I don't know, takes an hour or so to compute this phase diagram, maybe, yeah, or an hour and a half or so, depending how fine you want to be. And now you can actually use the symmetries, because you remember, you know where the bands close. So you know where these, depending on the parameters, how these envelopes of the bands kind of move. And you have them labeled by symmetry. So with this information, you can actually construct an analytical Chern number or topological invariant that tells you whether you're in a topological phase or not. And this is very similar to what was done before in crystals, where you have, for example, a phase that breaks time reversal and have some crystalline symmetry. You can also construct an invariant that tells you the Chern number. So we see this topological invariant modulo 3. And so this can still be done in amorphous states. And you can generate basically a phase diagram in a matter of seconds. And it really coincides with the numerical one. But the difference is that the symmetry analysis based on, again, local symmetries. So we are using that the local environment is the same, is generalizable to 3D or other symmetry classes in the same way as in crystals. While this Chern number, this local Chern marker, is not. So for example, if you had a 3D topological insulator with dimensional symmetry, you could still use this, but we cannot use this because we have dimensional symmetry. So the way it works is basically, you can label your states, your field states, with symmetry eigenvalues and do subtraction from a trivial reference. So we know that in the limit where W is 0 or where V is 0 is we have a trivial insulator. So we can construct this formula analogy with crystals essentially. There's another neat way of understanding this, but by projecting into momentum space. So you choose eigenvalues of well-defined momentum. So you're projecting out. Of course, your Hamiltonian is not translational invariant, so there's no momentum. But nonetheless, you can still do this, because if you project to a well-defined momentum basis, it's an overcomplete basis, so it's not a real useful basis. But in terms of topology, the eigenvalues of an effective Hamiltonian you can construct from this projection, the gap of this Hamiltonian closes at the same time as the normal as the actual Hamiltonian gap. And so you can use it as to track topological phase transitions. And this is something we do as well in the paper. I'm maybe not gonna go that with so much detail, but you can see a band inversion as well as a function of parameters in this case space. This was also used in the paper by Dan for quasi-crystals. We adapted it to amorphous lattices. Now, I also told you that there are average symmetries, which are also interesting. Here's an example from a paper that I like, but I was not part of. So in crystals, you have mirror symmetries, as I told you, that can protect topological states at the edge. So here's one. Here's the mirror plane that maps the up part to down part. If you break the symmetry, then the edge state is no longer protected. It's no longer gapless. It has a tiny gap, proportional to how much you break the symmetry. Now, in amorphous states, this actually does not happen. So if you have an average symmetry that is mirror, so on average you can map states on the upper part or sites of the upper part to the sites of the lower part. You have a nice gap closing here at the edge. But if you kind of tilt the edge a bit, you still have on average mirror symmetry. That nothing really has changed. So you still have protected by average symmetries a gapless state. And so this was shown in this paper for many types of symmetries. Basically, to say that amorphous states can be even slightly more robust than crystals on average. Okay, so this is my take-home message from the theory. Basically, we constructed models of fixed coordination. I just showed you the coordination 3 models, but we can construct others with 4 or 5. And we symmetry label the bands to calculate phase diagrams. And what we're doing now is try to generalize it to 3D and do it in a more systematic way with other and incorporating average symmetries to have a predictive theory for real materials. But this is long term because it's quite a heavy project. But nonetheless, a very exciting avenue. And maybe I don't know. Do I have maybe 5 minutes or?
You have about 10 minutes actually.
Oh, 10 minutes. Okay, perfect.
Yeah, sure. Around there, we'll have a bit of questions afterwards.
Okay. Yeah. So I just want to highlight that you can have coordinations that you don't have in crystals. So that's also quite interesting. So you can have topological phases in coordinate with coordination that you don't have in crystals. So those are already phases that we didn't know could exist. Okay, so now in reality, where are all these amorphous solids? So why we are creating this theory that can be predictive, which we don't have yet. We started thinking that maybe an easy way or an easy place to start from was to look at crystals that are topological, but have been grown amorphous, and whether those can be topological as well, with the hope that then we can go to crystals that are trivial and then maybe create topological insulators by amorphizing them. So I told you about bismuth selenide. Here's another kind of cut on the ARPIS, this photo emission experiment that now resolves spin. So you can see that spin up and spin down kind of live on different sides of a cone. And this kind of matches what the expectation from DFT would be. So some ab initio method. Now, here you immediately see already a problem. Like if you do an amorphous, you grow amorphous bismuth selenide and you want to plot a band structure, you cannot use K because K is not a good quantum number. So what do you do? So that's already, how do you find a Dirac cone in an amorphous bismuth selenide using ARPIS? Nonetheless, this didn't demotivate Paul and Sam, who were the PhD students behind these experiments. Sam on the ARPIS side and Paul on the growing and the transport, which I'll show in a second. They grew amorphous, or Paul grew amorphous bismuth selenide, which had already been grown, but not really understood, at least their properties in terms of topology by other groups. Oops, is this? So I think my here, sorry, my thing froze for a second. So you can see that there's no there's no order, at least no crystalline order, and the diffraction seems to be radially symmetric. So so this is a good indication that we have an amorphous system. By comparison, this is how bismuth selenide actually looks if you do this experiment on a crystal. So you see really clear peaks and a very nice crystalline lattice. This is not what we see, so we think that it's really amorphous. Now they did 3 types of experiments: transport, ARPES, and spin resolve ARPES. In transport, they looked at magnetotransport. So what you're seeing here is the conductance as a function of magnetic field. And at very low magnetic fields, the conductivity is high for low temperatures, and then kind of decreases with increasing magnetic field. And this effect is less pronounced at higher temperatures. And this is really what you would expect from a strong spin-orbit coupling system. It is called weak anti-localization. It means that that electrons become more localized, if you want, with magnetic field, but as you decrease magnetic field, there's some positive interference between time reverse past that increases their conductivity. And so this is consistent but not definitive proof that you have a topological surface state, but nonetheless quite hopeful signature, as I'll mention in a second what happens to other samples. So definitely in amorphous materials, you don't expect this type of behavior to occur because they're strongly disordered, and there have been many magnetotransport studies of amorphous materials that don't show this. And if you fit to a weak anti-localization type of formula, you'll see that basically at low temperatures, it looks like you have 2 decoupled channels contributing to transport, as happens in crystalline bismuth selenide, which would come from the 2 decoupled surfaces. Now, this itself is promising, but not really enough to say that you have a surface state and yet let alone a topological surface state. So in ARPES, you can try to access the surface and see how electrons, their energy disperses with respect to what. Now you cannot have momentum. So now what you do is you change the detector angle. And so you can still plot energy versus detector angle, which for long wavelength excitations could still be thought as a momentum. Just if you want, like close to gamma, an amorphous state would not care. So a plane wave will not care whether your lattice is amorphous or not. But anyway, you can plot the energy versus angle, and this is what I show here. And indeed, instead of showing some like completely washed out feature, as I'll show in a second for other samples, you actually see some structure. And this is what's quite surprising for us, because before doing this experiment, I was asking around a lot of ARPES people, and they would say, okay, I don't know of any paper that have studied ARPES. I believe ours is the first that studies ARPES in amorphous systems. But I would think that everything just washes out. And this is not what we see here. And in fact, if you take a cut, you see that the Fermi surface is spherically symmetric. I mean, this way you would expect, because the amorphous samples are isotropic, so you would expect something that is more or less spherically symmetric. And as you go down, this is taking a different ARPES energy, but if you go down, it kind of seems to shrink into a point. Now, from the theory point of view, you could take the model for bismuth selenide and actually amorphize it. There are like several ways of doing this, and calculate a spectral function as a function of a detector angle. And in fact, you can find still a very washed out bulk contribution, but still a pretty well-defined Dirac cone. And again, the reason is physically, or like an argument for this not to be surprising, is that the Dirac state is a very long wavelength state. that doesn't really care whether the lattice is amorphous or not. It's just determined by symmetry, by topology, essentially. Now, this looks a lot like crystalline bismuth selenide, and it's really tempting to compare this by just thinking that maybe this is the bulk band and these are the surface states that that kind of cross the gap. Now, to really say whether this is true or not, or at least consistent, we should be able to look at this in spin resolve ARPES, and this is what Sam did. Also, Sam took this other image as well, and you can see basically 3 regions where red and blue kind of switch places, indicating that that there is indeed some Dirac cone type feature in the energy spectrum. So here at the bulk, you have like this bulk states that are blue and red that are contributing a lot. So here's blue red. Then they switch partners because only the surface states contribute, red blue, and then again switch to blue red. So this we find we don't really find a gap. So this really looks like a topological surface state that we know from crystals. Now the reason, so here's a comparison between crystalline, basically plotted. This is also from Sam's group, so Alessandra Lazara's group, so they had bismuth selenide and they just plotted it in a way that we are not really used to, just with detector angle, and it kind of looks the same with some repetitions that I'll tell you about in a second. But the reason we're trying to, or basically now the reason this paper has been so long in the archives is that Sam and Paul did amazing background checks. In particular, they grew polycrystalline samples. And so the polycrystalline samples, first of all, don't look at all like the amorphous ones. They are completely featureless. They also don't have this weak antilocalization structure. Notice the scale is completely different to both the crystal and the amorphous. And so we think that this is quite good evidence that indeed the amorphous has some local. We have other probes in the paper that signal that seems to be some local order associated that survives the amorphicity and keeps the topology intact. And in fact, we're kind of exploring these features now with my student Quentin as Briand zone type repetitions, just like here. Essentially, what happens is that if you have a local order, you have a energy distance that is like a length scale that is still there. And so in momentum space, you can still think of Briand zones essentially. And here's maybe a better plot of this. So here's the experiment with some repetitions at higher angle. Sorry, this is well, I guess momento or angle. And in the theory, we also see if you plotted with respect to some characteristic distance, if you wanted the average to nearest neighbors, you can still see repetitions of the central Dirac cone. So this is for an amorphous model of bismuth selenide, and this is kind of a sketch. Okay, so this I think is all what I wanted to say. We've been trying to construct a theory that eventually will lead us to a predictive, to predict amorphous states in solids. We're not there yet, but I think it's quite promising to use local and average symmetries to try to figure out where we could find amorphous solids. And in the meantime, we've been collaborating with experimentalists from Berkeley, Alessandra Lanzara's group, and Francis Feldman's group to find topological insulator states in amorphous bismuth selenide. And well, as I say, we're trying to find cases where trivial crystals can lead to topological amorphous states, or try to revisit how do we actually probe this? How do we know that given I give you a chunk of material and it's amorphous, and how do you know that it's topological? And also we should add eventually, and we have added, for example, in the ARPES, I haven't shown it, but the effect of possible crystalline regions that you might have in the material. And the sky is the limit, strongly correlated phases. There's really everything to be done, and with the hope that we can find new physics that we haven't really classified yet. And so here I just leave you with this summary slide and take any questions that you might have. And thank you for your attention.
Thanks a lot for that. Questions?
May I, thanks a lot for your
Please, yes.
excellent talk. And may I ask a question about the current theoretical models of these famous topological insulators. So you mentioned about two different ways of realizing amorphous topological insulators. One is the local symmetry. Mm-hmm. The other is the averaged symmetry.
Right.
So do all the current theoretical models falls into these two categories?
Yeah, actually, that's a great question. So so right now, so basically all the published models, I think yes, but it's not the necessary condition. I mean, you could and I think we have models that you can have local order and then average order. So you can create, for example, graphene, for example, amorphous graphene. If you just take really amorphous graphene, you will have still, 3 neighbors. So there's some local order to that, and on average, it would be rotationally invariant. And so that's already a model that has both symmetries. I don't know if that answers your question, but I think that in general, it's not that you have both type of models. You can construct models with both symmetries. It's just that I think right now we have not used both symmetries at the same time to kind of figure out topological phases or predict or protect topological phases.
Okay, thanks. So maybe my another question could be, so in your model on the left-hand side top panel, so as long as we have this local symmetry, so for any kind of other configurations, we still have this topology, right?
Yes.
Okay.
If by other configurations, you mean like if I construct another lattice?
Yes.
Yeah. Then yes, absolutely.
Okay, thanks.
More questions? So I have is there a question? Sorry.
Okay. Yeah.
Yes, Joy, just go ahead.
Yeah.
Just go ahead.
I'm just curious about the system size of the model. I mean, is there any requirement for the system size to manifest the topology properties?
I think the system sizes, are essentially similar to if you would take like a crystal model, but just find it on all ends. You would like for the gap, the inverse length that the gap gives you will determine how localized the edge states are. And so you want the system size to be larger than that so that they don't talk to each other. But that, at least for these models, it's not that different from crystals.
So there is the minimum size for this model, right?
There's a minimal size, but
yeah.
So that if you make it too small so that the edges start talking to each other, then they would gap out just as in a normal crystalline topological insulator model. But I'm not sure if I'm understanding your question. Is that where you're at?
Yeah. I got it. Thank you.
More questions? So I had a kind of maybe very naive question. So of course your disorder that you've been kind of considering, with these random fixed coordination number kind of sites, z equals 3, 5, 4, 6. That's very interesting. I don't really know how to understand it within this framework, but there was a very interesting paper that Steve Simon and Mark Rudner wrote maybe last year about something called geometry independence. And the idea was very simple. So it was, if I take a tight binding model and I keep the tight binding hopping parameters the same on with everything, but I say disorder the sites, I move the sites all around, then this system is no longer crystalline. its Berry curvature is also changed because Berry curvature is dependent upon embedding in full three-dimensional space. But actually, if I look at the topological characteristics of this thing, it's the same. It doesn't change. Is there some kind of similar geometry independence type of argument that can be made? Because here you've kind of shown it, with numerical simulations. But is there some kind of similar type of because it seems to be quite sensitive to so in all respects your type binding hopping parameters are the same, and you added some kind of coordination number disorder. I wonder if there's something similar there whereby the index, the topological index, just has to remain the same because of this geometry independence principle.
Yeah, I think. So I think I know which paper you mean, and I haven't really thought in that way. But I guess there is some similarity. I mean, so maybe I can say a few things. So the model I presented is relatively simple. For example, in the bismuth selenide, we did something slightly more complicated, which was, so the bond strength actually depends on the angle, because you can have different orbitals overlapping, and this still shows topology. So you can still, there's a freedom of even changing the hoppings and keeping the topological gap, and I think, the way I understand it is that as long as you, I guess, as long as you're, by disordering, you're introducing some states in mobility. So you're basically closing the gap by just shoving in some states from strictly disordered, let's say, systems have states in gap states. And so as long as your disorder strength, let's say, doesn't really close or reclose the gap, let's say the mobility gap, then you still guaranteed to have the same topological phase. Now, whether there's deeper or like easier way of understanding this. So I would like to reread this paper, because I think one key thing that amorphous systems have that is different from, let's say, just disordering a crystalline lattice, is that there's not a canonical labeling of the sites. So you cannot really say, okay, I have sites 1, 2, 3, 4, 5. So I just order them, and then now I kind of move them a bit, but I keep the labeling, or I keep the or I add some on-site energy to those sites that are, because those models you can really kind of adiabatically move back to the crystal. But here, this is a bit different, because there's no continuous deformation from, let's say, an heptagon to a hexagon. I have to really cut a bond and like.
That's
and
right.
So
yeah.
So in this sense, these are a bit different. So I would like to see a bit the fine print of this paper, because I mean, indeed, they might include this case, but I'm curious.
No, I don't know. I'm not sure.
Yeah, but that's a very interesting remark. Yeah, absolutely. So very well posed.
More questions. More questions.
Please allow me to ask another very naive question.
Sure.
So for a crystal, we know that the less disorder, the lesser disorder is a lesser crystal. But how to qualify a amorphous solids?
So how to quantify the disorder in an amorphous solid?
I mean, for crystals, we can say that the more clean the crystal is, the better the crystal is.
Right.
So, and we have maybe better topological characteristics.
Mm-hmm.
So for amorphous solids, how to compare different configurations and say which is better representation of the topology?
I see. That's an interesting question. I think so. For example, I always tend to use the honeycomb lattice because it kind of is visually very appealing and kind of easy to imagine. But like for me, for example, you could think of, if you insist on having fixed coordination, you can think of the density of hexagons and seeing, okay, you know, whether to go from a crystal to an amorphous, you can change how many hexagons you have. And so the perfect amorphousness would be basically no hexagons, or very few hexagons. And you can start seeing like how topological phases are affected by this. A different answer could be you know, some scaling argument. If you sit on a site, how many sites do you encounter as you increase a radius? And this there's actually a lot of people studying what are called hyper uniform lattices, which you know, there's some power law distribution of how many sites you encounter as you move away from one, and the structure factor. And these are quite interesting, for example, in photonic lattices, because they want to understand how to make still insulating states so that have gaps, but they're not necessarily periodic photonic crystals. And so they play around with this concept of hyper uniformity. And so one might say that if you have a hyper uniform lattice, then you're very much an ideal amorphous state. So, I mean, I think that there's no, maybe possibly like in crystals, there's no like one parameter that tells you, okay, this is the cleanest crystal, no? Because you can have, I don't know, you can look at mobility, or you can look at I don't know, other parameters like hot electron lifetime. I mean, those two things might not be the same. Like if you shine light and they respond, and how does this relax, or how does a material conduct just a DC frequency that might not be the same, and you know, what is cleaner? Then there are always different parameters that you can choose to say that whether a system is more clean than others. And I think here in amorphous cases, it's maybe even richer. You can, depends on your definition of what is an ideal amorphous system, then you can find many measures of this.
I see. Yeah. Thanks a lot.
Yeah, that's a very good question, actually. I mean, I honestly, I don't know the answer. But I feel it's a complicated issue. Yeah.
Okay, unless there are more questions, I think we've had a fairly Arpit. There seems to be a question from Arpit.
I have a very naive question. See, so you were able to write down a Hamiltonian H as a function of K, because I think there was an assumption that even the solid is amorphous, but it has some local. It still respects the symmetries locally, right? So for example, considering your tight binding model, did you can we check at what number of nearest neighbor hoppings will the tight binding model break down? Or
so okay, so first of all, maybe a clarification, because maybe I went slightly fast on that slide, but like, if you can always project, let's say if you have a Hamiltonian that is not translational invariant, you can always project into plane wave states and see what you get. Like this is something that, in fact, it's kind of like what the ARPES does. You shine some plane wave, which we call light, and then it projects the electric wave function into that. And so this you can always do. Now, and then this can give you, depending on the information you're looking for, this might be too crude. For example, if you're looking at how different Ks couple to each other, you're throwing all that information away. But if you're just looking at, if you're just interested if the gap closes and reopens, then it seems that this is enough to project into a plane wave basis. Now, whether the states that you see in this projection, kind of what do they mean with respect to the real system? You know, we use them as a tool to diagnose topology, but the ones close at gamma, close to k equals 0, they should be still there, let's say, in the real system, because again, they're like a long wavelength type of excitation, so they shouldn't care so much about amorphousness. And regarding your question on local symmetries, I think local symmetries, what they assume is that all sites, the definition of my definition of working definition of local symmetry is that is a symmetry that it's an on-site symmetry, or like a site, what we would call a site symmetry. So a group of orbitals, or maybe a cluster of sites even, that that is a building block of your amorphous lattice. So they might be oriented in different ways or whatever, but within a site, you can always find a symmetry that kind of rotates different atoms into themselves, or different orbitals into themselves. And so in that sense, it doesn't matter how many neighbors or nearest neighbor hoppings you include. You just have to make sure that your sites are always equivalent. So if I go to this side or I go to that side, it doesn't matter. You always have, like, let's say 3 neighbors or 5 neighbors, or 3 first neighbors and 5 right now. So, or maybe you want to preserve that on average. So then there's a question of which, at some point, there's a length scale where you have to start thinking about symmetries on average. So, but in terms of let's say point group symmetries, what you want to impose is that each site is essentially equal to any other, so that you have this idea of band edges that are still symmetry labeled. I don't know if I answered your question.
You answered it. Thank you.
Great, super. So thank you very much, Adolfo. This was a very interesting talk. So thanks for coming, everyone. So the seminar is over. So thank you very much. Very interesting. Thank you.
Thanks for the discussion. It was great. Very nice ideas.
Let me just stop the recording.